Gravitational wave astronomy. Imagine space itself changing shape, not because a planet is moving through it, but because space-time is being stretched and compressed by the motion of enormous objects in the universe. This is the basic idea behind gravitational waves. And in 2015, scientists detected these waves directly for the first time. That discovery opened an entirely new way of studying the universe. For most of the history of astronomy, we have studied the cosmos through electromagnetic radiation, especially light. Telescopes collect visible light, radio waves, infrared radiation, X-rays, and gamma rays. Each gives us different information about distant objects. But gravitational waves are fundamentally different. They are tiny disturbances in the geometry of space-time itself. And the idea goes back to Albert Einstein. In 1915, Einstein introduced general relativity. According to the theory, massive objects curve space-time. The Sun, for example, creates a curvature that affects the motion of Earth and the other planets. But when massive objects accelerate dramatically, that changing curvature can propagate outward as a wave. These are gravitational waves. They travel through the universe at the speed of light. One of the strongest sources is the merger of two black holes. Imagine two black holes orbiting each other. As they orbit, they lose energy through gravitational radiation. Their orbit gradually shrinks. They move faster, closer, and faster, until eventually they merge into a single black hole. The merger produces a powerful gravitational wave signal that travels outward across space. But by the time that signal reaches Earth, the effect is extraordinarily small. So scientists needed an instrument capable of measuring incredibly tiny changes in distance. That instrument is LIGO. LIGO stands for the Laser Interferometer Gravitational Wave Observatory. It uses two long perpendicular arms, each several kilometers in length. A laser beam is split into two separate beams. One travels down one arm, the other travels down the second. The beams reflect from mirrors and return to the central detector. Scientists can compare the returning light with extraordinary precision. When a gravitational wave passes through the detector, space-time stretches slightly in one direction and compresses in the other. The distances between the mirrors change by an incredibly small amount. LIGO is designed to detect that change. And we're talking about a distortion smaller than the width of a proton. Then, on September 14th, 2015, LIGO detected exactly the kind of signal scientists had been searching for. It was called GW150914. The signal came from the merger of two black holes roughly 1.3 billion light-years away. Those black holes had been orbiting each other, losing energy through gravitational waves until they finally merged. The resulting gravitational waves traveled through space for about 1.3 billion years and eventually reached Earth. LIGO detected them. It was the first direct detection of gravitational waves, and it confirmed a remarkable prediction of Einstein's theory. But the discovery was important for another reason. It created an entirely new branch of astronomy. Traditional astronomy observes objects through electromagnetic radiation. Gravitational wave astronomy allows us to study the motion and mergers of extremely massive objects through the distortions they create in space-time. It's especially useful for studying black holes, because black holes themselves don't emit light. We can often infer their presence from their effects on surrounding matter. But gravitational waves give us another way to study the black holes directly through their interactions and mergers. Then came another major milestone. In 2017, scientists detected gravitational waves from the collision of two neutron stars. The event was called GW170817. This time, gravitational wave detectors weren't the only instruments watching. Telescopes around the world detected electromagnetic radiation from the same event. Scientists could therefore study one cosmic event using multiple types of signals. This became known as multi-messenger astronomy. And it produced an important discovery. The collision provided strong evidence that neutron star mergers can create heavy elements such as gold and platinum. So some of the elements found on Earth were likely produced in extremely violent cosmic events long before our planet existed. And gravitational wave astronomy is still developing. Scientists are detecting more black hole mergers and neutron star events, and each detection gives us information about the population of these objects across the universe. But future observatories could take us much further. Ground-based detectors such as LIGO, Virgo, and Kagra are sensitive to particular ranges of gravitational wave frequencies. A future space-based observatory called LISA is designed to detect much lower frequency gravitational waves. Its 3 spacecraft will form an enormous triangle in space, with laser beams measuring tiny changes in the distances between them. This could allow scientists to study massive black hole systems and other sources that are difficult to detect with ground-based instruments. There is also an even more ambitious possibility. Gravitational waves may contain information from the very early universe. The oldest light we can observe comes from hundreds of thousands of years after the Big Bang. But gravitational waves could potentially carry information from much earlier periods. If scientists eventually detect a primordial gravitational wave background, it could provide clues about the conditions of the universe during its earliest moments. That would give us a completely different way to investigate cosmic history. So, gravitational wave astronomy isn't simply about detecting invisible waves. It's about expanding what we mean by observation. For centuries, we studied the universe primarily through light. Now, we can also study the movement of space-time itself. Black hole mergers, neutron star collisions, and potentially events that we haven't discovered yet, can all leave signatures in gravitational waves. And every detection adds another piece to our understanding of how the universe works. The most fascinating part is that this field is still very young. We've only just begun opening this new window. And somewhere in the universe, there are almost certainly gravitational wave signals waiting to be detected. The question is no longer whether the universe produces them. We know it does. The question is, what will the next signal reveal?